So, welcome to the dynamics session, and James will present the first talk.
Good afternoon. As mentioned, my name is James. This is joint work with Georgios, Piliouras, also at SUTD. As the title suggests, we're going to talk about some common update rule applied to a very common class and well-studied class of games. Traditionally, when we talk about game theory, the first solutions people sort of think of is the Nash Equilibrium. And it's sort of this idea of this being the solution, what we need to focus on. That's the idea that I really want to dispel today. While it's true that many of the algorithms we use sort of converge to the Nash Equilibrium, this convergence is really only in a time average sense. Player strategies only on average converge to Nash Equilibrium. The truth of the matter is that a lot of the algorithms we use don't converge to Nash Equilibrium on a day-to-day basis. And this is going to have a lot of implications, both positive and negative, in the applications of learning theory. So in today's talk, we're going to be studying the dynamics of these games, this day-to-day behavior, and we'll touch a little bit on those implications in the application of learning theory. So games, we could go, of course, through the mathematical model, but I really want you guys just to think about it as the interaction of two or more players. And in this talk, we're going to be focusing on zero-sum games, games where one player wins and one player loses. So there's like a common examples I can give you. People playing poker, someone bluffs, someone decides to call the bluff. Companies compete for market share. One consumer gained is a consumer lost by another company. There's, of course, this popular setting of generative adversarial networks. For instance, you can think of two competing networks, one that tries to distinguish between virtual images and real images, and the adversarial network that actually tries to generate virtual images that are indistinguishable from the real ones. But specifically in this talk, we're going to be focusing on normal form zero-sum games, where we have this payoff matrix, and one player is going to sort of try to maximize the payout, and the other will try to minimize it. Common examples are rock, paper, scissors, matching pennies. For instance, in matching pennies, if both players play heads, the row player gets a payout of 1, he wins the game, and the column player loses the game. If they both play tails, if they match, again, player 1 wins, and player 2 wins whenever they mismatch pennies. The solution to this game, how we typically study games, is through Nash Equilibria. And rather focusing on utilities, I want you to think about what they are sort of from the perspective of player interactions. They're fixed points. They're points when players will no longer update their strategies. It's sort of static behavior. It's stable. In the case of matching pennies, the Nash Equilibrium is, well, I'll play heads with 50% of the time, tails 50% of the time, and then no matter what my opponent plays, he or she will get the same payout, and therefore they have no incentive to sort of deviate from their strategy. Regrettably, we don't always know the payoff matrix. We don't always know the Nash Equilibrium, so we have to do something else on a day-to-day basis. And the consensus is that we're going to use some sort of no-regret algorithm. And of course, no-regret algorithms have nice guarantees on utilities, but for the sake of this talk, we're going to sort of focus on this nice result in game theory, in zero-sum games, that no-regret algorithms, when they're used in zero-sum games, the time average behavior is actually going to converge to Nash Equilibrium. And I sort of think this is why people sort of focus the framework of game theory through the Nash Equilibrium. On average, this is indeed what players do. But in reality, we're going to see a lot of algorithms don't actually do this. Players aren't necessarily going to converge to Nash Equilibrium. There's going to be a much more rich, more nuanced set of trajectories that we're going to see when players update their strategies with these no-regret algorithms. And there's a lot of behavior we're not going to be able to capture just by focusing on the Nash Equilibrium. We actually need to study these day-to-day trajectories, these day-to-day strategies. And I think sort of the perfect metaphor for this is the solar system. In terms of the solar system, the sun's at the center of it. It's a fixed point. The sun doesn't orbit about itself. It's sort of the stationary point in our solar system. When we think about our planets, they move around the sun. The Earth, for instance, is approximately at average in the sun. But when we talk about the Earth, we don't look at its average position. We don't pretend like the Earth is in the middle of the sun when we study it. I mean, it's sort of stupid. We get the right idea for its average position, but everything else we sort of lose. If we want to understand Earth's surface temperature, for instance, the average position is sort of ridiculous. It's not quite that hot on the surface of the Earth. And therefore, when we understand these systems, we focus on those orbits, what happens from year to year, day to day, how they evolve over time. In the same way, it's going to be important that when we talk about game theory, these learning algorithms, that we focus on them with respect to the trajectories that create. Some of these algorithms might actually converge to Nash equilibrium. Some of them might look a little bit more like the orbits around the Earth. We might actually cycle around a Nash equilibrium. It's even possible we could converge to the boundary or even do something much more chaotic. And depending on what these trajectories actually do, it's going to have implications when we go to apply these learning algorithms in sort of real-life applications. So let's look at these trajectories. And I suppose the first thing we need to define how we're going to actually update our rules. For this talk, we're going to talk about follow-the-regularized leader algorithms. And follow-the-regularized algorithm is perhaps the most commonly used class of algorithms. We sort of select a probability vector, a mixed strategy, that's going to maximize some combination of a cumulative payoff as well as the colors are off a little bit. And a regularization term that's going to give us our no-regret guarantees. Some examples are gradient descent. The regularizer we use there is just the L2 norm, the Euclidean distance. Of course, multiplicative weights, where we use a negative entropy function. And I do want to make a note here to actually get these no-regret guarantees. We need this learning rate, this eta or this epsilon, to decay over time. But for now, we're going to go and look at the problem with a sort of a constant learning rate, and we'll address that later. So let's apply this algorithm to matching pennies and see what happens. It turns out the strategies don't converge in Nash equilibrium. We actually get something completely different. Oh, wow. I can't keep my hand steady. The strategies are actually repelled from the Nash equilibrium. They cycle outwards, spiral outwards, and move toward the boundary. It's sort of weird to say the Nash equilibrium is the solution to this game because the Nash equilibrium is actually the furthest thing from our final solution. We end up getting something on the boundary and because the Nash equilibrium pushed things away. And our theoretical results actually match this. Not for just matching pennies, but for any game with an interior point Nash equilibrium. And for multiplicative weight update, or really any follow-the-regularized leader algorithm, we're going to get convergence to the boundary. And that's going to hold even if players use different regularizers. Say if you use gradient descent and I use multiplicative weights update. And of course, this is for the case of interior point Nash equilibrium. We do sort of complete the results. In the event there's no interior point Nash equilibrium, we'll still converge to the boundary, but we're going to do something more. We're going to converge to the smallest space that contains the set of Nash equilibrium. And then within that space, we'll again converge to the boundary. And there's sort of a few conditions that I think we'll eventually be able to fix up. Currently, it's for any game selected with sort of probability 1, but I think that's an issue that we'll be able to address sort of later on. I do want to go over the proof for the first one because I think it has some nice parallels to what we look at with general no-regret dynamics. In order to show this result, we're going to, of course, show the strategies move away from the Nash equilibrium. And we're going to do this by examining the Bregman divergence with respect to the regularizer used in the follow-the-regularized leader algorithm. Now, typically how Bregman divergence is used, it's typically used in regret proofs. We put an upper bound on it in order to imply that our regret doesn't get too large. We're actually going to go a different direction. We're going to put a lower bound on the Bregman divergence and show it's going to actually increase. Specifically, we're going to show that there's some constant d where in each iteration of multiplicative weight update or follow-the-regularized leader, it's going to increase by that constant. And as a result, the Bregman divergence is actually going to go to infinity, implying convergence to the boundary. And that's sort of the general idea of proof. We'll go, of course, some of the technical details. The first thing, we're going to assume that it doesn't get close to the boundary for contradiction, which is going to be our final sort of part of the proof a little bit later on. But since we don't get close to the boundary, we can ignore the boundary constraints when we're solving this optimization problem. We can ignore the non-negativity constraints of those probability vectors. And sort of just make our problem unconstrained, we'll also do a substitution. We'll get rid of this constraint, the sum of the variables equal to 1, and just sort of remove one of our variables. And we end up with an unconstrained optimization problem that's fairly easy to solve. Our optimality condition is simply the gradient time t is equal to the gradient the previous time plus the payoff vector created by my opponent. In using this optimality condition, we're going to be able to say a lot about the Bregman divergence. So let's look at that. We know the regularizer we're using is strongly convex with respect to some parameter. And we're starting to take advantage of convexity to relate that, the time step at time t, to the time step at the gradient time t minus 1. And we'll update our algorithm. And what we see is the Bregman divergence is actually the regularized Nash equilibrium minus the regularizer at time t minus the gradient time t. And we're actually really close to having that for time t minus 1. We have the Nash equilibrium term, we have the regularizer, and we have the gradient, but regrettably it's at time t. Fortunately, those optimality conditions we gave a relationship between the gradient time t and the gradient time t minus 1, so we can plug that in. And these three terms here precisely correspond to the Bregman divergence at time t minus 1, plus sort of this amount proportional to how much the strategies actually change. And then there's sort of this payoff from a couple of games we play. And those payoffs are actually going to cancel out. Because our strategies are Nash equilibrium, when I play my Nash equilibrium, we said that it doesn't matter what my opponent plays. And therefore, instead of looking at the payoff when I play my Nash equilibrium, my opponent plays a strategy time t minus 1, I can just assume my opponent also plays the Nash equilibrium. So we can sort of substitute this in, and we multiply out. We get the decided term. Finally, we're just going to add together the two divergences of the two players. And what happens is, because the game is zero-sum, well, when we add this together for both players, they cancel out. The sum of that game is 0 when they both play Nash equilibrium. And at time t minus 1, those are also going to sum up and become 0. And we'll see that the Bregman divergence actually increases by amount proportional to how much the algorithm actually changes those preferences. So we already have the Nash equilibrium repels strategies. Now we just need to show it repels by enough. And that argument's a little bit simpler. We've said the Nash equilibrium is the only static, the only stable point, and therefore players actually have to do some sort of update. And therefore this step size is positive. And then just using a compactness and continuity argument, we can sort of bound this by some positive constant. And we can say that in each iteration, the Bregman divergence increases by at least some constant d. We sum that up over infinity, and of course we get a diverging Bregman divergence. And as a result, that sort of contradicts our assumption we never got close to the boundary. And that completes the proof that these Nash equilibria push player strategies all the way to the boundary, at least when we have sort of this interior point Nash equilibrium. And again, the proof for non-interior Nash equilibrium is a little bit different. We won't be going over that. But what I do think is important is sort of linking this back to those no-regret algorithms. We said to get no regret, we actually need a decaying learning rate. Currently, our result only holds for this constant learning rate, this epsilon 0.5. And for those of you familiar with the literature, the typical rate we choose, typical learning rate we choose is this 1 over root t. And we actually see something really interesting in the pictures, in the simulations. If the learning rate decays slower than a rate of 1 over root t, we converge the boundary. And if it decays faster, then we don't converge to the boundary, despite all three of those being no-regret algorithms. We get slightly different behavior. And in fact, we formally show this by showing that the convergence of the boundary occurs only if the sum of the learning rates squared goes to infinity. So we show these two pictures, implies that this one doesn't go to the boundary. And it turns out this special case, this typical case we use 1 over t, it goes to the boundary just really, really slowly. And the idea of this proof is sort of similar, but instead of bounding the increase of divergence by some constant d, we're actually going to bound it by sort of a function of the learning rate. It's approximately the learning rate squared. Some other extensions. We can actually use different learning rates for different players. It doesn't really have a significant impact. It just sort of stretches or compacts the trajectories we look at. The results are going to even hold in network games, games between lots of players where players are nodes and the edges between the nodes represent other zero or constant sum games between those players. And we see here in all these results, the Nash equilibrium really isn't the solution. The Nash equilibrium is somewhere here in the middle. But the truth is, on a day-to-day basis, we move outwards. We avoid the Nash equilibrium. We're repelled by it. And like I said, that's sort of going to have some implication in a lot of other areas. The first thing we think about is human behavior. And we imagine that humans sort of converge to Nash equilibrium. That's the common belief. But this means that they can't possibly using FTRL. They're having to do something to sort of curve their dynamics inwards towards that Nash equilibrium. And I think it's sort of interesting what we can learn about human behavior and sort of leverage that for our algorithms in order to get maybe something that actually converges curves inwards. The next sort of interesting area is understanding of the algorithms themselves. We've said that we study these games through the framework of Nash equilibrium. As I've said a few times, that's not the right way to look at the problem because we avoid those equilibria. The fact is that we actually drift away from them, we converge, and we wander around somewhere close or on the boundary. And I also think this has a lot of areas for nice results. For instance, how can we leverage this dynamics to learn more about the algorithms we're using? Can we use these dynamics in order to improve the learning rates that we have? Can we find or observe cycles of these player trajectories in order to understand and predict reliably what people are actually going to do when they use these algorithms on a day-to-day basis? And finally, and perhaps most importantly, this is going to have a large implication on our applications of these algorithms. There are indeed algorithms that converge to Nash equilibrium. And we, of course, FTRL doesn't. And one is not necessarily better than the other. Just because the time average converges to Nash equilibrium, and player utility is in fact pretty much the same when they use either dynamic, how society views these outcomes can vary greatly. So first of all, let's think about that GANs model where we have two competing algorithms, one trying to distinguish between virtual and real images, and the other one is trying to create images that are indistinguishable. If we actually converge the boundary in these sort of games, if we cycled outwards and played extreme solutions, your algorithm that's trying to distinguish is going to go through long stretches where it says every image is real and every image is false. Or long stretches where it said every image is real, and then other long stretches where it's going to say every image isn't real. And that's sort of stupid. We want something a little bit smarter that's more adaptive. We actually want something that converges to Nash equilibrium. On the other hand, there's instances where converging Nash equilibrium might not be the best thing. For instance, imagine two vendors selling ice cream. They're both selling vanilla and chocolate. The Nash equilibrium is they both sell vanilla chocolate about half the time. And when we think about sort of implementing this solution, well, on a fourth of days, both the vendors are going to sell vanilla. Fourth of days, both the vendors are going to sell chocolate. So on half the day, consumers are only going to have one choice of what kind of ice cream they like, which I think is terrible. But if we think about these extremal solutions instead, for instance, if on odd days the first vendor sells vanilla and the second vendor sells chocolate, and on even days they do the opposite, the first sells chocolate and the second sells vanilla, then the time average still converges to Nash equilibrium. The player utilities are the same, but the output for society is much better. Consumers always have a choice between vanilla and chocolate on an everyday basis. And therefore, in this case, we'd prefer some sort of algorithm that performs at more of these extreme points rather than at the Nash equilibrium. So some final remarks on future work. I sort of already touched on the first two in the previous slide. We're also hoping to sort of generalize these results for things besides bilinear games, more complicated objective functions. And I've also recently found sort of this deep connection between physical systems and these learning dynamics. The fact that I chose the solar system was actually intentional because the same forces that drive these dynamics in our solar systems and masses and springs and pendulums, it turns out to be the exact same forces that drive the trajectories we see in game theory. And I hope that's sort of a compelling reason to take a more nuanced look at these games, not just focus on Nash equilibrium. And if you'd like to hear more about this, we can talk about it offline. You know, you guys could invite me to a job talk, or you could even join us out at SUTD. It's a beautiful place, as a few audience members can tell you. But thanks. I appreciate your time.
Questions while the next speaker sits up?
Yeah.
So is the spiraling out the beyond? So suppose I just project the trajectory from high dimension to 2 dimensions. Is that always a spiral out?
So in higher dimensions, it's a little more complicated because converging the boundary in 2 dimensions means that we defines the cycle itself. In higher dimensions, that is something we need to understand a little bit better. Simulations sort of suggest nice behavior, at least rock, paper, scissors. It will move outwards, of course. But whether it's this sort of clear, cyclic, almost cyclic-like behavior is a little more questionable. Any other questions?
So you talked about when your parameter was like 1 over c, it like very clearly what happens.
So it's sort of the threshold point. And changing my analysis doesn't matter, but 1 over t to the third, for instance, a slower rate of decay.
Yeah, as long as
It will converge to the boundary. Anything faster will not. It's sort of the threshold point, which I think is really interesting because it's the best choice for minimizing regret, but it also represents this threshold of whether or not we converge to the boundary.
Yeah, in your pictures, you had always one Nash, but in general, there could be even 2 players. There could be a whole polytope. So what happens in those switches?
As long as there's one interior point, the strategies will be repelled from all the Nash equilibria, roughly the same way.